Let's study 10th standard ICSE Physics, Chapter 6, Spectrum. Section A, Deviation, Dispersion and Spectrum. We have studied that light bends twice while passing through a prism because it has two refracting surfaces, AB and AC. And since the two surfaces are not parallel, hence the emergent ray is not parallel to the incident ray. So there is a deviation. Refraction happens at point Q and R respectively. Air to glass bends towards the normal, and then glass to air, it bends away from the normal. And the angle between the incident ray extended and the emergent ray extended, this angle is called the angle of deviation, because in the absence of the prism, the ray would have gone like this, but now it has deviated like this. So this total deviation is actually a sum of the two individual deviations. There is one deviation happening at one surface and the other deviation at the other surface. So geometrically we can prove that the total deviation is delta 1 plus delta 2. This formula is not that important, but the factors are, this total angle of deviation depends on three things. It depends on the angle of incidence at the first surface. The angle of incidence at the first surface will decide the total deviation. Secondly, it depends on the angle of the prism, that is this vertex angle on top. And it also depends on the refractive index of the material of the prism. Diamond would deviate light differently compared to water or glass. This also means that the deviation depends on the wavelength of light or the color of light. Wavelength is an objective property which we can measure. Color is a subjective property which depends from person to person. The exact color cannot be scientifically described. For me, this might be dark blue, but to somebody else it might be a little lighter shade of blue. It's all comparative. Next, let's study the dependence of deviation on the color of light. If we pass white light through a prism, and that's a narrow beam of white light, we make sure it's a narrow beam by passing it through an aperture in a window. That's a very small hole. So white light is split into its 7 constituent colors, Vibgyor. Why does this happen? Well, that's because white light is actually electromagnetic radiation composed of various wavelengths. And we can see the wavelengths from 4000 angstroms to 8000 angstroms, the wavelength that is. Now in air or in vacuum, the different wavelengths, light of different wavelengths has the same velocity, 3 into 10 raised to 8 meters per second. But the moment they enter another medium like this glass, their speeds decrease in differing amounts. Violet light will now be slowest compared to all the other colors, and red light will still have the highest speed, even though it would also slow down compared to its speed in air. Because of this, the refraction takes place at different angles. The deviation is different for different colors. Not only that, at the second surface, this difference between them is exploited further. And they separate even further, giving you a band of colors which is called the spectrum, which can be seen on a screen. And this is the cause for rainbow colors also, seen in the sky during monsoon season, or in cases where you view a tube light with a glass or a plastic ruler. It's simply splitting of light, white light, and this is called dispersion of light. What is the cause of dispersion? The cause is that the refractive index of any medium is different for different wavelengths of light. Different colors of light refract differently. Different colors of light are deviated by different angles. Violet bends the most. Red bends the least. Red is deviated the least. Violet is deviated the most. That's why we have these colors separated. Their speeds became different inside the glass. That is why their unity was broken. So remember, lower the wavelength, like for example, violet color's wavelength is 4000 angstrom. More is the deviation. And more the wavelength, less is the deviation, because more is its speed. Now remember that the splitting of white light or dispersion is taking place only at the first surface. At the second surface, it is not splitting further. it's just getting refracted and they are separated further. The distance between them increases. So dispersion as well as refraction takes place on the first surface, but on the second surface only refraction takes place. Yes, deviation again takes place on both the surfaces. When I say deviation, it simply means refraction. But dispersion means splitting of white light into 7 colors. That happens only at this point. Also, when you see the band of colors on the screen, we don't have clear-cut boundaries separating the colors. It's a continuous transition from one color to the other. Now solve both the numericals in the numericals book, and even in solved examples, the 4th and the 5th one needs to be solved. Pretty straightforward numericals. For example, here the frequency is given, speed is given, calculate the wavelength range. So we've got 2 numbers to solve. So here I have solved the sum for you. Wavelength we know is velocity upon frequency. Now how to solve such sums? One method is, let me borrow 3 zeros from this power. So I'll make it 3000, and I'll borrow 2 zeros from here to make it 375. So this becomes 10 raised to 5 and this becomes 10 raised to 12. So that I can now reduce it and get 8, and then 10 raised to 5 minus 12 will be 10 raised to minus 7 meters. So that's 8 into 10 raised to minus 7 meters is the wavelength, which is same as saying 8000 angstrom, as they have mentioned, but you need not convert it. You can leave it like this. It's an SI unit. Secondly, there is another frequency given. So again, we have to find the wavelength. 3 into 10 raised to 8 upon 7.5 into 10 raised to 14. Let me use a different method here. So into 10 to get rid of the decimal. So that's 30 upon 75, and I have not touched these powers at all. Keep it as it is. This becomes 0.4 into 10 raised to minus 6 meters. So that's the answer. But for uniformity, it's better to have the same power here and here. So what I'm going to do is I'm going to do into 10 and divide by 10, so that this becomes 4 into 10 raised to minus 7. Alternatively, you could have written this as 0.8 into 10 raised to minus 6. It really doesn't matter as long as it is correct. Write the final statement. The wavelength range is 4 into 10 raised to minus 7 meters to 8 into 10 raised to minus 7 meters. Write that statement. So that's how you solve such sums. Now, what is a very interesting fact is that visible light is actually a very small member of a family of electromagnetic waves. Radio waves, microwaves, infrared waves, which are also called heat waves, UV rays, X-rays and gamma rays seem to be so different. They have different effects on living and non-living things. And yet they belong to the same family of energy called electromagnetic energy. This entire family is called the electromagnetic spectrum. The only difference between them is the difference in their wavelength. Otherwise, all their properties are same. Laws of refraction, diffraction, reflection are obeyed by all of them. They have the same velocity in vacuum, 3 into 10 raised to 8 meters per second. Gamma rays have the highest energy because they have the smallest wavelength, just 10 raised to minus 2 nanometers. That's extremely small. And below that, their frequency is the highest. X-rays, they have a lesser frequency and a bigger wavelength. Then comes UV rays. Then we have VIBGYOR. So when the electromagnetic waves have a wavelength, or rather a frequency greater than that of violet, we call that ultraviolet, which we can't see. We can only see VIBGYOR because our eyes are evolved that way. And if the wavelength is more than 800 nanometers, now we call that wave as infrared waves or infrared rays. Again, we can't see that. Some organisms can see these parts of the spectrum, like bees can see UV rays and snakes can see infrared rays. Even we can see infrared if we have the night vision goggles or night vision camera. We can see the heat being given out by bodies or anything. Bigger wavelength, then it is called microwave. And the biggest wavelengths, 10 raised to 10 nanometer and beyond that, they are called radio waves. So they have different uses. So this is the visible spectrum, VIBGYOR, 400 to 800 nanometers or 4000 to 8000 angstroms. And beyond them is the invisible spectrum. Here are some properties common to all of them, which I talked about. A few more points which I missed. All these waves are not deflected by electric and magnetic fields at all. because they are not made up of any charged particles. They don't have mass. They are pure energy. And they're all transverse waves, not longitudinal waves. Sound is a longitudinal waves because sound has compressions and rarefactions, whereas electromagnetic waves have crests and troughs. But again, understand that these are not mechanical waves. These are pure energy electromagnetic waves. Next, we have to study certain properties. Properties of UV light. UV rays are unique from the rest of the family because they can pass through quartz, but they're absorbed by glass. So if you want a UV spectrum from a source, suppose a source is giving many electromagnetic waves like UV rays, gamma rays, visible light, but I want only a UV rays to come out of it. So I can have a quartz prism instead of a glass prism, because quartz prism will block the other radiations, but they will allow UV rays to pass through it. So that's a good reason why UV bulbs have a quartz envelope instead of glass. UV bulbs have many functions. They can kill germs, they can attract flies and mosquitoes. The speed is same, of course, as visible light. They are usually scattered by the dust particles present in the Earth's atmosphere. So thankfully, a lot of UV rays are blocked by the dust particles as well as the ozone layer. So the amount of UV rays falling on us is quite less. So the chances of skin cancer are less. And yet we should apply sunscreen lotion to protect ourselves from the UV rays. They obey all the laws of reflection and refraction, of course. They strongly affect the photographic plate. So there are certain photographic plates which have some chemicals on them, like silver salts, etc. When UV rays fall on it, then a reaction takes place and an image is formed. That's how photographs were taken in the past. Nowadays we have digital cameras, but earlier we had photographic plates. They also produce fluorescence on striking a zinc sulfide screen. So if you have a screen with a chemical called zinc sulfide, and if UV rays fall on it, then they will glow. They can even glow in the dark, like your radium wristbands do. That is an example of fluorescence. Harmful effect is it causes skin cancer if exposed for a long period. Uses, as I said, for killing germs, detecting the purity of gems, eggs and ghee. How? That you need not know. And in producing vitamin D in food of plants and animals. So we should expose ourselves to the sun for short periods of time so that vitamin D is synthesized in our skin. Next, properties of infrared radiations. Again, they also travel in straight line like light. They also have the same speed. They obey the laws of reflection and refraction. So when you have a convex lens, a magnifying glass, out in the sun with a paper under it, the paper catches fire, not just because of the light from the sun, which we can see, but mostly because of the heat from the sun, which is actually infrared radiations, which we can't see. They are focused onto a point on the paper and the paper catches fire. They do not affect ordinary photographic film. So that is one way to differentiate between infrared and UV rays. However, in case of infrared radiations also, a specially treated photographic film with some special chemicals may be affected by infrared radiations. They are absorbed by glass, but they pass through the rock salt. So that's a way of getting infrared rays. Use rock salt. For UV rays, what was it? Quartz. We can even detect it by the heating property using a blackened bulb thermometer. For example, if you want to know if infrared rays are falling on you, but you can't see them, so what you can do is you can keep a thermometer and the bulb is blackened because black absorbs a lot of light as well as infrared radiations. If you see the temperature is rising, that means there are these invisible infrared radiations present falling on this thermometer. They are scattered less by the Earth's atmosphere because of their long wavelength. So remember, the intensity of scattered light is inversely proportional to the fourth power of wavelength. Simply speaking, more the wavelength, less is the scattering. This is interesting. What this means is, the sky is blue because blue color is scattered more than the other colors. Blue has a small wavelength compared to yellow or red. So smaller the wavelength, more is the scattering. So from every corner of the sky, you see blue light entering your eye. And that's why the sky appears blue. But violet has the least wavelength, even less than blue. Is it scattered the most? More than blue? Yes, it is. But our eye's retina is more sensitive to blue color rather than violet or purple. That's why the sky appears blue. Otherwise, there is a lot of violet light also out there, which we can't detect so easily compared to the blue light. So red light is scattered the least. That is why the sky is never red. Only when the sun is setting, it appears to be red at the horizon, and there is a reason for it, which we'll study shortly. But it's very clear that red, infrared, which have a very large wavelength comparatively, they are scattered the least, so they can penetrate deep inside the atmosphere even in a fog. This is very useful if you want to send signals to your friends in the military. They use infrared radiation signals. Also, danger signs are always red in color. Even the traffic signal, red means stop. Why have they chosen red? Because red travels the farthest. Red can be seen from far away. Blue light will travel up to a certain distance and then get scattered in the atmosphere. But red light will travel a large distance before getting scattered. So you can see a red sign from far away compared to a blue sign. That's why red is used in signaling. Also the greenhouse effect, which can sometimes cause global warming as well. If you remember, they are actually trapping, the greenhouse gases trap the infrared rays coming from the Earth's surface. Greenhouse gases like carbon dioxide. These infrared rays are nothing but heat rays, but they are of the long wavelength. At long wavelength, infrared rays are trapped by greenhouse gases, thus heating the Earth's atmosphere and the surface. What are the uses of infrared radiations? Well, it's used for therapeutic purposes, that is medical purposes, which doctors would know about. They are used in photography at night because even if there is mist and fog, they are not much scattered. They can penetrate to a large extent and travel farther in the air. Infrared lamps are used in dark rooms for developing photographs. So when you develop the photographic plates, the chemicals are very sensitive to light. So in an ordinary room, whether there is a ordinary light falling, it may damage the photographic plates chemicals and you won't get the proper image. You need a dark room, protected from light. But in complete darkness, you can't see. So we can use infrared lamps. The whole room would look reddish. It will give us some visibility at least. And fortunately, it hardly affects the photographic film, which we studied. Only if it's a specially treated photographic film, only then infrared radiations can affect it. They're also used as signals during the war, as they are not visible to the naked eye, but with machines we can detect it. And also they are not absorbed much in the medium, they travel far away. They are used in remote control of television and other gadgets. So when you press the remote control, you see that red bulb at the tip glowing for a second. Some signal goes to the TV and the TV is switched on or the channel changes. That signal is invisible, but it is infrared. And why we chose infrared? Because it can travel the farthest in air. So this table will be a good way to revise whatever I've taught right now. Remember, infrared radiations don't cause fluorescence either. Only UV rays do. Visible radiations, nope. Solve both these numericals. Finally, scattering of light, which I've already introduced you to. Scattering is a process of absorption and then re-emission of light energy by the dust particles and air molecules present in the atmosphere. So, if you see here, the rays of light are scattered by the dust particles and the air molecules. Don't think of it as a reflection, no. What's happening is the dust particles and air molecules first of all absorb the light, and after a split second they re-emit the light. This is called scattering. And which color is scattered the most? Violet. The air molecules of size smaller than the wavelength of the incident light absorb the energy of incident light and then re-emit it without change in its wavelength. So if the air molecules or any scattering molecules are very small, smaller than the wavelength of incident light, light can have a wavelength of say 4,000 angstrom or 8,000 angstrom, which is extremely small. But if the air molecules are smaller than that, then they will not discriminate between the various colors or various wavelengths. They will scatter all the wavelengths equally. I beg your pardon. Actually, they do discriminate because they are air molecules of size smaller. What I meant is that they re-emit it without changing their wavelength. So if they have absorbed, let's say, light of wavelength 4000 angstrom, then they will also scatter light of 4000 angstrom. But the intensity of the scattered light depends on the wavelength. Simply speaking, smaller the wavelength, more is it scattered. So red light with the maximum wavelength in the visible light spectrum will be scattered the least, and violet light with the least wavelength will be scattered the most. That is why the sky appears blue, as I explained. So this results in a few phenomena. For example, why is the sky white at noon? When you look overhead, directly above yourself at the sky, it doesn't appear blue at all. Near the sun, the sky appears white. That's because if the sun is overhead, then the rays of light have to travel a very short distance through the atmosphere to reach your eyes. So the scattering is very less. On the other hand, when the rays come at an angle and travel a long distance across the atmosphere, then the blue light is scattered more and the red light is scattered less. So the sky appears blue. And at the same time, I would like to point out that when the sun is setting, at that time, the distance traveled by the sun's rays is maximum. Here's an example. So at noon, here you are standing. Here the rays of light have to travel very short distance, so scattering is very less. So the sky appears white. Check it out at noon. At any other time, the distance traveled is quite more through the atmosphere. So a lot of scattering happens and the sky appears blue. At sunset or sunrise, the distance to be traveled by the light is so much before reaching your eyes. They have to pass through the atmosphere such a long distance that not only blue light, but even red light is scattered. And so now the sky appears reddish. And the rays of light reaching your eyes, which color is that? Red. All the blue light would have already been lost, scattered. And red light is also scattered, but at least some of it can reach your eyes. So that is why, what is the color of the sun at sunset or sunrise? It is reddish, because only red light is able to reach your eyes. All the other colors, blue, green, yellow, orange, they have scattered. But at noon, what was the color of the sun? Check it, it's white, because all the colors are able to reach your eyes. Hardly has any scattering taken place. What if there was no atmosphere at all? What would be the color of the sky? If you are on the moon, for example, and you look up, yes, the sun will appear white, of course, white. There will be no scattering happening. There is no atmosphere here. And what about the rest of the sky? What would be the color? Black. It appears black. Space appears black because it has no air molecules or dust particles to scatter the rays of light. So no light enters your eye from any direction other than that of sun, so it appears black. The absence of light is darkness. But what about clouds? Again, back on Earth, clouds appear white. Why is that? Well, I said that when the air molecules or the dust particles are smaller than the wavelength of light, then they will discriminate between the colors as far as the scattering effect is concerned. Red light is scattered the least and violet light is scattered the most. But the clouds have aggregates of water molecules and ice particles which are larger than the wavelength of light. So they will not discriminate. They will scatter all the colors equally. So when all the colors of light enter your eye, it appears white, and that is why clouds are white. And finally, as I said, red light is used for danger signal because they travel the farthest with least scattering, since their wavelength is highest. And even remote controls use red light or infrared light.
Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.